standard deviation is coming right off the heels of a variance. So because variance is computed using a squared deviation, the units for variance are squared units for the data. So if you were trying to figure out, like what is your average commuting time or something like that, you have a mean commuting time, and then you're trying to figure out, well, how does commuting times kind of vary from that mean? If you use variance to figure that out, variance is giving you units in squared miles, which doesn't make sense if you're trying to figure out a distance in miles. Why would you compare it to square miles? So for example, once again, in the battery lifetime example, if we were talking about those batteries, so we're talking about them lasting so many hours, their variance would be in squared hours. And what's a squared hour? So in most situations, it is better to use a measure of spread that has the same unit as the data. So this is where we are going to have what we call our standard deviation. So to do this, we simply are just going to take the square root of the variance, and the quantity that is the square root of variance is what we call the standard deviation. So the standard deviation we are going to note as an S or a sigma. So actually the notation we have for variance actually comes from standard deviations. So standard deviation is S and variance is that S squared. So remember, variance is the S squared. So what variance is actually the square of the standard deviation. So to get that standard deviation, all we're doing is doing the square root so we can get back to the standard deviation. So like I said, notation for variance is just a square of standard deviation. And to get a standard deviation, you just need to do a square root of variance. But I want to make another little note here. So when we're talking about variance is an average. So it's an average squared distance or deviation from the mean. So the idea of doing that square root is it's not completely algebraically sound, but for essentially what it is that standard deviation is going to be the average distance, or just the average deviation from the mean. So the means slightly different thing. So when you're talking about variance, it's doing those square distances. Standard deviations is essentially, in essence, is an average distance that you have from the mean. So once again, if we're talking about battery life, the batteries that we said that their mean was 4 hours, but the standard deviation is going to be like roughly like 1.5. I think it's 1.4. What that is telling me is that what I'm expecting is that on average, that deviation from a battery life of 4 hours is only about 1.4 on average. So I'm expecting that most batteries are going to be, have a battery life somewhere between would be, let me see, like 2.6 and 5.4, because both of those are about 1.4 from the mean. So it's kind of telling me, like averaging out the distance, the variations that we're seeing in that data. Okay, so just some examples here. So if we wanted to figure out the population variance for those temperatures in San Francisco, we know that the standard deviation for those temperatures was 14.083, and that'd be degrees Fahrenheit squared. If we want the standard deviation is going to be the square root of that 14.083, and we're going to get a 3.754. 3. So I'm going to take a moment here, and I'm actually going to go back and look at that data with the temperatures. So if you look at San Francisco, we had a mean temperature for San Francisco was 57.5 degrees Fahrenheit. And what we just said is that my standard deviation is roughly about 3.8, so maybe about 4 degrees. So if you're looking at my distribution of temperatures here, what we're saying is that what we're expecting is that this is about average. So our smallest that we have here is this temperature. So my minimum temperature is 51 degrees. And what we're seeing here is that the distance from here to here, from your mean to that minimum, is about 8 degrees. So what we're seeing here is that this standard deviation is about half that because it's kind of averaging out that distance. So we have other temperatures in here. There are going to be between that minimum temperature and that 57.5. So what it's doing is it's taking those temperatures and kind of figuring out an average of those temps and tell me, okay, so what I'm seeing here is that though the mean temperature is 57.5, on average, how much that temperature varies from that center is about 4 degrees. So it's averaging out that distance from the center. Kind of same thing on this side. We see our maximum value is going to be that 63. So that's about, well, let me see, that's about 5 degrees above. So it's like not always going to work the same on both sides. But like I said, so this data's kind of skewed a little bit in one direction. But essentially the idea is that we're centered here and we're just kind of trying to average out this distance that we're seeing from the center. And that is what a standard deviation is trying to do. So when it's giving me this range of about 4 degrees, it's saying that's on average, I expect that I'm going to see the deviation from that degree from 57.5 degrees to be about 4 degrees one way or the other. Now, sometimes we have really cold days and sometimes we have really hot days. But like I said, we're just kind of averaging it out. If we go back to those batteries, so we figured out that the variance for the batteries was 2 hours. That was a sample. We have x squared is 2. So if I want to figure out s, my sample standard deviation, I just square root of s squared, so the square root of 2, which is 1.414. So if I go back to my batteries here, my data is kind of spread out as 2 is my lowest, 6 is my highest, 4 is right in the center. We're kind of like trying to average out this distance that we're seeing here from the center. And what we're saying is that the average distance from the center which is my 4, is roughly about 1.4 hours. It's all really that standard deviation is doing. So it's kind of like averaging out. We know that distance is 2, but not everything is 2 away. We got some things that are 5 away. We have some things that are 3 away. So we're just trying to, like I said, just find an average to that. Okay. So clearly, variance and standard deviations are not something you want to calculate by hand over and over again. It took a little bit of time just to do 3 points when we were looking at those times for the batteries. So what we can do is you can use the TI-84 and 1 var stats will tell us a sample standard deviation and a population standard deviation, like we see here. So this is those San Francisco. So what we see from San Francisco is what we're getting right around here. If I wanted my variance, all I had to do is just square those values. So if I square that sample standard deviation, I'm going to get a rounded answer to this because We're not gonna get this all fitting in here. 19.18 squared. This is about somewhere around here, maybe. If we square the other one, so my 17.5. So this one, if I square it, I'd get like 306.25. So like I said, that's just these temperature, these numbers squared. These are my variances. So this is for a sample. If this is sample data, and this is for a population. So whichever one you choose, sample or standard deviation, is based on the data you had. So you should be told whether your data is a sample or it's a population, and then you know if this is what you're looking for standard deviation for this. And then you know what to square if you want your variance. So this is for Excel. So we're going to take this data. We already looked at San Francisco. We're going to take St. Louis's temperatures, and we want to compute the standard deviation and the variance. And one of the best of the ways that we can do that would actually be, trying to find my data here, is going to be, you can take another picture of it. Just a second. Yeah. I'd suggest like taking a picture of that. That's what I just did. Then we could go put this in the calculator. But if we put this in our calculator, it's going to save us a lot of time. So bear with me a second. I'm going to move over to a calculator. Okay. Now I know this is not as great as it could be, but this is my free calculator I have. So if I want to enter that data, those temperatures, you are going to go right here where it says stat and list. So we want to go to edit. So I could just hit 1 and it's going to take me right to my list. Okay, so I need to clear out my list. So if I use my wheel here and I go up 1, hit clear, enter, that'll clear my list. So from there, I just want to enter in those temperatures. So we had, oops. So if you need to go back and get rid of something, you just move back to where you need to go and hit delete, because I just entered in the wrong one. But for St. Louis, we got 30. And you just hit enter. 35, and we hit enter. 44, enter. 57, enter. Supposed to place 66, enter. 75, enter. 79, enter. 78, enter. 70, enter. 59, enter. And then we have 45, enter, and then 35, enter. So we have all that data in there. And we should have 12. So if we hover over this one, we see a 1, it says 12. So that tells me that's my 12th data point. Okay, so I'm going to second quit and get out of there. So then you're going to hit stat again, and you're going to move over to calculate, and you see 1 for our statistics. So just hit 1, or you can just hit enter after you hover over it. So make sure that list 1 is in there. Like I said, if you have to change the list, right here in the blue is list 1, list 2, list 3. So I'd hit second 2 if I wanted list 2. But I don't. I want list 1. So I'd hit second, list 1. Enter, enter. So we don't need a frequency, and we calculate. Make it a little bigger for us. We could read it. Okay. So this was population data because it was all the months that we had. So we're going to use this one because we should have a population standard deviation. From a right standard dev. So that would be my sigma, it should be 17.08 or 09. So if I want my standard deviation, I just have to square that. We could do that right on here, actually. So just go to the bottom of everything, so we're out of there. Make this smaller again. I'm just going to put in my 17.09. And then right here, you see this little caret. I hit that, put in a power of 2, hit enter. So now we see that my population variance is going to be 292 point, we'll say 07. Okay. Also, just going back to one of our statistics, enter. Also notice that you have your mean in here, which we ideally pointed out before, but you're going to have your mean. This is going to be either population or mean or standard deviation, or sorry, population mean or sample mean. It always puts it as sample, but it's either, because they're calculated the same way. Okay, and then like I said, we have our standard deviations here. We picked the one we have. We got the numbers, the number size. We also have the summation of our x's. We have the summations of our x's squared. We got a bunch of information that are going to happen here. So we're actually going to bring this back again, because if you scroll down, you know this is more information, and we're going to use that in the next section. Okay, for a big comparison, we got SF for San Francisco, SL for St. Louis. Wrong bed. What we're seeing there is that, remember that San Francisco's temperatures are a little more pushed together. I had that right the first time, sorry. Those are a little more pushed together. So these are the standard deviations, or the variances. So we see variances was significantly bigger for St. Louis than it was for San Francisco. But we're going to see the same thing also for standard deviations. So because San Francisco temperatures didn't vary that much, they only had a range of 12 temperatures. And we're sent, so we look for that center, the average change from that center, which was 57.5, I believe. The average change from that center was roughly about 4 degrees. St. Louis, its center was at 56.8, I think. But we have a much more larger, change in that. So in here we saw at most, like, we got 51 to here, so that's almost like 6.5 degrees. That's the biggest like change that we see, but the biggest change we see in here, I think, is 16 degrees. So there's a lot more variety in the St. Louis. So my standard deviation is going to be much larger because I have a lot more that I can change by. Oh, not 16, sorry, like 26, like almost a 30-degree change is what we can see in here. So this is roughly about half that 3-degree change. This is roughly half of that, like almost 7-degree change. So we're getting like that average that we're seeing from that dispersion of the data. There's one problem here for you guys to try to attempt. So a credit card company is studying the levels of credit card debt held by college students. They select 8 students at random. Their balance in dollars are $342, $541, 1,652, 43, 87, 137, 0, and 418. So this is their credit card debt among, well, it was at 8 college students. So we want to find the standard deviation of these balances. Okay, so add that data in here. If we just go to stats, go over to calculate one for our statistics. I'm going to make sure I have list 1 in there still. So we see here that with a sample, we're going to use this one right here. That would be my sample. So as far as the sample standard deviation, which we're going to call S, is, we're gonna round this to a, nearest cent here, but it's 500, yeah, $540.58. Okay. I'd like to point out also, though, that our mean is $402.05. Not 5 cents, I'm sorry, 50 cents. That would make a little bit more sense. Okay. So what really happened here is like we're averaging around 400, but we have this one right here. Really, 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 really large number, right? If you look at most of my data, everything else around that, like at most we got 500. So we're like looking at a range between 0 and 500. So that mean it got pulled off center, right? Because we're probably really like averaging without that in there, somewhere around maybe $300, something like that, a little less than that. But this definitely is pulling this way off course. That also means that the standard deviation is also getting pulled way off course as well. Because on average, if you're looking from the center of that, most of the data is within a couple hundred of your center of 400. It's just that one data point that is significantly far away. It's like over $1,000 away. It pulls that whole standard deviation to a much bigger number than we would necessarily like it to be. That's going to bring us to this part here. Standard deviations are not resistant to outliers. So just like means are not resistant. So recall a statistic is resistant if its value is not affected much by extreme values, extremely large, extremely small values in the data set. The standard deviation is not resistant. That is, standard deviation is affected by extreme values. And that's partly because means are not resistant. So we're using a measurement that is not resistant to make another measurement. That other measurement's not going to be resistant. So means are not resistant. Anything calculated from a mean is not going to be resistant. So once again, standard deviations is one of these things that we tend to use when we have those bell-shaped curves because we don't have to worry about those extreme values as much.